Hello, my name is Siawoosh Mohammadi. I'm giving the last presentation in the symposium. I will focus on the calibration step, and my presentation is based on some of the stuff that Jennifer has nicely introduced. I will mainly talk about 3 studies that we have performed and try to address 3 different issues here. The first one is the calibration that is currently standardly used for myelin imaging sufficient to estimate the tissue fractions? Then we will look at whether we need also a calibration to estimate the tissue fractions from diffusion-based quantities. And finally, we will introduce a new calibration approach, which accounts for more calibration parameters than the standard one. And I will sum up. Okay, let's start with the myelin imaging question. This is based on a simulation study where we generate ground truth G-ratio maps, and we want to see what goes wrong if we use the standard calibration approach. To do that, I will shortly now sketch the simulation study. So we have some ground truth histological myelin volume fractions, and we have histological axon volume fractions. And from there, we plot them against each other, and we estimate a curve, how they are corresponding to each other. And using then this curve, we can exactly generate a ground truth G-ratio, as shown here, using the normal MR G-ratio formula. In a second step, we estimate linear relations for 3 different myelin imaging biomarkers to relate the MR-based myelin imaging markers to the histological ground truth again. We fit curves. These are now linear relations that we fit, and they will have different offsets and different slopes. Here shown in different colors. And then we use now these MR G-ratio, MR-based myelin volume fractions, so these curves, to estimate again the G-ratio, but this time from the MRI-based data. So just sketched again, they might look somehow different to the ground truth one. And here, basically, we use again the MR G-ratio formula, where the axon volume fraction is untouched as compared to the gold standard G-ratio, but the myelin volume input now uses the MR-based one, so these relations. To generate these relations, which I have sketched before, we will use a rich data set based on 3 model mice, with the TSC2 mice, which is strongly hypomyelinated. So we have most of the myelin is gone. And then we have the hypermyelinated P10 mice, and which have more myelin, and then Victor and healthy are somewhere in between. And we look at 4 different regions of interest, 3 in the corpus callosum and 1 in the anterior commissure. And using that, we can now generate these 2 relations here. And that's what is done here. So in different colors are the different mice for the different region of interest. And this is the fit using this heuristic equation. And using now this fit, we can calculate the ground truth G-ratio, which would look like this. The next thing is we want to now estimate the myelin markers from different myelin imaging approaches. To that end, we just shortly recap how an MRI voxel is composed of, so the tissue model for myelin imaging. On the one hand, we have our water pools, free water, CSF, non-myelin water in the cellular cells or in the extracellular space, and the myelin water trapped between the myelin sheets. The first method, the myelin water imaging method, estimates the water trapped between the myelin sheets and gives us a linear relation with a very small offset. The second method is a bound pool fraction, which is a larger offset, but also a nice linear relation. The third one is proton density imaging, which is has a negative slope and a small offset. If we take 1 minus this term, then we have again a positive correlation to our myelin volume fraction, and the term is then called myelin MTV, macromolecular tissue volume. These three relations are now used to generate basically our MR-based G-ratio curves, which are then compared to the gold standard. And this is done in this Blunt-Altman presentation, which is shown down here, and this is the corresponding scatter plot. In blue, we see the points, the G-ratio points from the ground truth plotted against the myelin marker. And this is the bound pool fraction based G-ratio. In green, we have the myelin water fraction based G-ratio, and in black, the MTV based G-ratio. And here the ceiling effect comes because the axon volume fraction can be negative, and then basically the square root in the square root of the full expression will be negative, and that's of course not possible. So we seal it to 1 when we have invalid values within the square root. The next step is the calibration. So the standard calibration works as follows. We neglect the offset here, which is the same as if we have basically this term here. So here we basically factored out this myelin volume fraction term in order to have just a scaling effect. This is only a scaling effect which is independent of the myelin volume fraction if this term alpha is much larger than this ratio here. And then we can basically estimate the scaling factor, which is sufficient to relate the MR-based myelin volume fraction to the histological one, and from that also to correct for the G-ratio, of course. Here is the results when we do this calibration, and you can see that for the bound pool fraction, nothing changes. Basically, it's still very badly related to the ground truth. Whereas for the MTV and the myelin water imaging approach, we find almost no qualitative changes. It's a bit stretched. And when we look at the Blunt-Altman results, we see that the errors getting on average bigger for all of them. So in summary, the calibration using only scaling in our simulation at least doesn't really improve the correspondence between the ground truth G-ratio and the simulated one. Now to the second point, do we need calibration also for diffusion MRI? This is a study where we, which I just shortly introduced because of time. We have 4 different calibration scenarios. The first one is basically what is at the moment standardly used, that our diffusion-based proxy for the axonal water fraction is directly measuring axonal water fraction. The second one is that there might be a pool of unmyelinated axons which is not captured by the axonal water fraction, and we need an offset term to account for that. And the third term is a scaling parameter that is necessary. We showed in our paper that this is related to the compartmental T2 decays, which Jennifer nicely introduced previously. And then the last model basically says that you need both the scaling and the offset. Now we basically plug in these different models in order to estimate a proxy for the axonal volume fraction, and we will compare this MRI-based axonal volume fraction, which we call FA, to the histological one using the same data as before. So as said before, we will look at this residual sum of squares between the histological measured axon volume fraction and the MRI-based, and to account for the degrees of freedom of the different calibration models. So we will use the Bayesian information criteria, where K is the number of of the model parameters, which is 0 for no calibration, and which is 2 for linear calibration. In our preprint, we looked at different models based on the standard signal model of diffusion MRI. But here I will just focus on the one with most parameters, biological parameters that are estimated, which is the Watson WMTI Watson model. And here are the results. So what you see here is different combination of these parameters, and we have a few more which I didn't introduce here, which is basically that we have two different offsets for the model mice. We grouped them in two different groups. Basically, the highly unmyelinated axons, they were strongly different, and they got an extra offset term. Anyway, the result is that the best combination is the linear one, so in green, using an offset term for the highly unmyelinated axons and a scaling factor. But what we also see is that the second best is actually when using only the offset term, so neglecting the scale. And that's the same for some other models as well, which I didn't talk about here. And here, just to visualize how that looks like for the scatter plot, you see without calibration that basically the TSC2 mice are almost not correlated to the between the histological measure and the MRI measure here. But when we use a calibration, we find a nice correlation. Okay, so last point, can we improve the calibration? So what we looked at here is a standard calibration where we have only scaling, and another calibration where we have 3 calibration parameters, the scaling on the myelin side, the offset on the myelin side, and additionally an offset for the diffusion imaging side. Here we use the Akai information criteria to compare the two models with each other, and we use to generate the MRI-based G ratio. We use the myelin water fraction imaging approach, which was the best one, and also the WMTI approach, which was also very good. So here are the AIC comparisons, and you see that the 3-point calibration is better in terms of AIC than the single-point calibration. When we look at the scatter plot, we also see that there are more, the green one would be the 3-point, is more around the line of unity than the single-point. And when we quantify this, we see that the error is also on average smaller in the 3-point calibration, and also the standard deviation across for the 3 parameters that we estimate, they are comparable between single-point and 3-point. So in summary, we have shown in these 3 studies that first, we need an offset for myelin imaging, at least for the methods that we looked at. The single-point calibration is especially bad for the bound pool fraction, at least in our simulation. The second point, we also should account for calibration constants when using diffusion MRI-based volume fractions. And here, especially offset is important, but accounting for offset and scaling is the best way to go. And third, we have 3 calibration parameters introduced, and that works better than using only 1 calibration parameter. So future work needs to look at a realistic way to estimate these 3 calibration parameters, and or to find better proxies for myelin and diffusion-based volume fraction estimates. I would like to thank my co-authors and you for your attention.